Hi, in this video we're going to go over the physics journal about power. So what is the question that's guiding this is what is the difference between doing 100 joules of work quickly and doing 100 joules of work slowly, right? So essentially in this case you've accomplished the same task, whatever that is, that took you 100 joules, but you've done it at a different rate. So the big idea here is that power is a concept that describes the rate at which you do work. So it, right, the number of joules per second. So again, sorry, there you go. So that means that the equation for power would be the work divided by the time. So um, work again is the kind of the task that you accomplish, lifting something up, accelerating some, speeding something up, stretching a spring, something like that. And then you just divide that by the time, the t, the amount of time that it takes to do that. Keep in mind that work is also energy. So change in energy, that could be final energy minus initial energy. So it could be your final gravitational energy minus your initial gravitational energy. If you're lifting something up, it could be your final kinetic energy minus your initial kinetic energy if you're speeding something up. Um, so it could be your final elastic energy minus your initial elastic energy if you're speeding something up. So the power is joules per second. So it's measured in joules per second. Again, kind of the amount of work you do divided by how quickly you do that, the time. And then for some reason, they have renamed a joule per second something called a watt. And that's fine, except that it makes it sound like a watt doesn't sound like a rate, right? If I say like, oh, 10 watts, that sounds like an amount, not a rate. And so I think it's best to kind of keep in your mind, remember that 1 watt is a joule per second. So anytime you're seeing the word watt or the unit watt, you're thinking about a joule per second. So one watt is equal to 1 joule per second. That's going to help you remember that it is a rate, meaning like how quickly energy is transferred, as opposed to an amount of energy. So another unfortunate thing about the watts is that the variable in the equation, um, this right here, right? So that's a variable. That W stands for work, which is the amount of energy. It has units of joules. The W that would like follow a number like that one right there, like 1 watt, that W stands for watts. It's a unit and it's telling you like how many watts it is. So just keep in mind that we have two capital W's kind of working in close proximity here. One of them is a variable and it's going to represent the amount of energy. The other one is a unit and it's going to represent, well, the unit for joules per, is going to represent joules per second. Kind of an example of where we might think about this. So watts commonly show up in like light bulbs is probably the place that you're most familiar with this. So if we had like, let's say a 60-watt light bulb, like one of those old incandescent light bulbs, um, they put out 60 joules of energy per second, or they use 60 joules of electrical energy per second. So that's kind of what that means. We also measure power in horsepower, HP. And this is obviously most commonly thought of in cars, right? We measure cars in terms of horsepower. And that would be like basically how quickly can that car, um, you know, turn chemical energy of gasoline into kinetic energy, right? I mean, when you think of a high horsepower car, it's how quickly can it accelerate, which is basically how quickly can it um, convert things into kinetic energy, right? The higher the horsepower of the car, the faster it can basically create, kinetic energy and accelerate quickly. So 1 horsepower is equal to 745 watts. So it does, a horsepower is quite a few watts. A watt's a pretty small unit. Horsepower is a pretty big unit. So there may be some situations where you only have force and velocity, and if that's the case, right, we can take our equation. Power is equal to work times by time. Work is equal to force times by distance, right? Just go back to the work notes if you forgot about that, but work is equal to force times by distance. And then I can just kind of rewrite this, right? Because that doesn't really matter the order of multiplication. I can have this F over here, and then I can have this D over T. And the reason that I would do that is because distance divided by time is velocity. So power is also equal to force times by velocity. So Let's look at these example problems here. So it says consider a 60-watt porch light. So how much energy is required to leave it on overnight? So when it's asking about how much energy is required, it's really asking about the work, right? So if we take our equation, power is equal to work divided by time, and we just multiply by t, you're going to get work is equal to power times by time. Just simply multiplied both sides by t there, right? So we can take the power, it's a 60-watt light bulb, so 60 watts times by the time. Now the problem is because 60 watts is joules per second, I really need to change my 8 hours. I need to change that into seconds. So 8 hours, so I'm going to do 8 times by 60. That's going to turn that into 480 minutes. And then I'm going to change it into multiply by 60 again. That's going to change it into seconds. So that's really equal to 288,000. No, sorry, 28,800 seconds. So that's going to go here. The reason it has to be in seconds is because 60 watts is 60 joules per second. So my time unit must also be in seconds here. So that's going to give us 1,728,000 joules, right? It's amount of energy, so it's measured in joules. So there we are with that. Now, here in the Pacific Northwest, right, most of our electricity comes from comes from a dam, and basically, right, a dam is going to work by um, holding water back here, and then basically allowing that water, you know, to flow through your dam, and thus, you're basically getting the gravitational energy, you're releasing the gravitational energy, right? We, for the most part, have gravitational energy stored back here. So basically, the question is how much mass of the water do we need to let through Grand Coulee Dam to generate this amount of water, or this amount of energy, right? So gravitational energy is equal to mgh. So we need to get at least 1,728,000 joules worth of gravitational energy. We are looking for how much mass we need to drop down there. How much water basically do we need to release? And it's 168 meters tall. So do a little math here. 9.8 times by 168 give you 16,406.4. Divide both sides by that, by 1646, and you're going to get 1,000, basically 50 kilograms worth of water. So 1,050 kilograms is, roughly about a ton of water. So to keep your porch light on, all night, the dam has to let through about 1 ton of water. So, all right, so that seems like a lot, right? 1,000 kilograms. I mean, I realize that we're not super familiar with meter or mass, sorry, with kilograms, but 1,000 kilograms is approximately equal to 2,000 pounds. I mean, very roughly. And so, like, this just seems like a lot. That seems like a lot of water to have to um, let through the dam. So, if energy costs approximately 12 cents per kilowatt, which is probably kind of what it is here in, that's fairly close to what it is here in the Pacific Northwest. We might be slightly lower than that. We might be about 10 cents. 10 to 11, it depends. It's not quite that straightforward. A kilowatt hour is a unit that we haven't seen before. It's It's kind of a really dumb way that we measure energy. So right, like if you think about this, a kilowatt, right? That's the power times by a kilowatt hour, right? Kilowatts times by hours. Hours is a time. If you have a power time, right? A P times by a T, that's going to give you a W. Just look back up here, right? So that was how we did this one. And so basically, the unit a kilowatt hour is the amount of work done, which is the amount of electrical energy basically that you've used. So we just have to figure that out. So we need to get our answer um, of you know this work up here from part A. We need to basically convert that um, into kilowatt hours instead of joules, right? So it's we have it in joules, we need it in kilowatt hours. And probably the easiest way is to just kind of recalculate that. Um, so but use the proper units. So basically, we need to find 60 watts and convert that into kilowatts. So that would be zero. You do that just simply dividing um, by 60 watts is equal to 0.06 kilowatts. And then we already know that, right, your T, we need that in hours, so that's 8 hours. And if we look at the units that we're going to get kilowatt hours. So we'll get the proper units there that we need to figure this out. So that's just 0.06 times by 8, and that's going to give you 0.48 kilowatt hours. So to leave your light bulb on all night is 0.48 kilowatt hours. So each one of those kilowatt hours, um, right, is going to be $0.12, so 12 cents, times by the number of kilowatt hours you used, your light bulb used. Oops. And got the H up there. So the cost is going to equal 0.12 times by 0.48. It's going to cost you approximately, I'm going to go ahead and round here, but uh, 6 cents approximately. So not too, right, pretty cheap. So it's funny how it kind of puts things in perspective there that man, it seems like 2,000 pounds or 1,000 kilograms worth of water that we have to let through the dam, and over 1 million, almost 2 million joules of energy for this light bulb to run all night. And ultimately, what does it cost you? Only 6 cents. And of course, that is for an old school, light bulb. Our more modern LED light bulbs are going to use significantly less um, energy than that. So like I don't even remember, but it's like somewhere in the like 5 to 8 kilowatts instead of 60 kilowatts. So obviously a light bulb like that, a modern LED light bulb is going to cost you significantly less to keep on. So yeah. Anyway, hope that's kind of a cool example problem to kind of wrap this up. I hope that you enjoyed that. Thank you very much for watching, and as always, let me know if you have any questions. Thanks. Bye.